Alright, so we're going to continue talking about substitution reactions. So we've been talking about making carbon-carbon bonds using carbanions. We either deprotonate an alkyne to make that nucleophilic carbon, or we deprotonate the alpha carbon of a carbonyl to make that negatively charged carbon that can then go attack a positively charged carbon to make a carbon-carbon bond. So let's continue talking about substitution reactions. And so if you want to convert a carboxylic acid into a methyl ester, we're going to use something called diazomethane. And so this is a new reagent that you all haven't seen before. It's written out as CH2N2. And so what does this look like? Well, we have a nitrogen in the middle here, and then our two hydrogens from our carbon are coming off. And so diazomethane looks something like this. And then it also has a resonance structure where we can move these electrons down and move these onto this carbon. If we draw that out, then we have a species that looks like this shown here. And so this carbon has a negative charge on it in this resonance structure. And so this is able to deprotonate carboxylic acids. We don't want to use diazomethane in the lab though, because it might explode. So if any of you all go on to be organic chemists, you're going to want to use trimethyl diazomethane in the lab, or TMS diazomethane. Here's the chemical formula, but for our purposes on paper, you can simply write diazomethane, CH2N2. So this type of reaction looks like this, where we take a carboxylic acid functional group and we convert it into an ester functional group where it has a methyl group off of the side. This carbon right here comes from the carbon in diazomethane. And so if we go through the mechanism of this, remember that diazomethane, one of its resonance structures looks like this, shown right here. So this negatively charged carbon comes in and, so I'm going to draw this hydrogen out. It's going to come in and deprotonate our carboxylic acid. Remember that proton transfers are one of the fastest reactions we have in organic chemistry. And so if we can do a proton transfer, we will. In this case, an acid wants to lose a hydrogen. Indeed, we lose it to this carbon. And so this gets us to an intermediate for this compound up here. Again, I'm going to use pH to represent phenol. And then we get our carboxylate anion shown here. And then we now have a neutral carbon because it's made a bond to this hydrogen. And so we have something that looks like this shown here. And so nitrogen, although I didn't write it on my list of leaving groups, is the best leaving group there is. And so now this carbon right here is attached to a nitrogen. It's partially positive. And so our carboxylate comes in and does an SN2 reaction on this carbon and kicks out into or nitrogen gas. And so what does this give us as a product? Our oxygen is now bound to a carbon, oxygen bound to a carbon. This carbon is no longer bound to this nitrogen, and so we've lost into gas. So we use diazomethane to make methyl esters from carboxylic acids. And this works because nitrogen gas, N2, is the best leaving group there is. It's extremely stable and it's a gas, so it bubbles out of solution once it's formed. If you think back to Le Chatelier's principle, N2 is one of our products. If we're removing some of that, then it drives our reaction towards the products. And so that's what keeps this, makes this reaction happen. So moving on in our discussion of substitution reactions, this one we've seen before, but we didn't really give it a name. And so this is called the Williamson ether synthesis. So this reaction was developed by a chemist named Alexander Williamson in 1850. And so that's why we call it the Williamson ether synthesis. This is nothing new. You've seen this before. We just haven't called it this. And so we take an alkoxide shown here, so some type of deprotonated alcohol, some type of alkyl halide, and we get an ether as our product. So alkyl halide plus alkoxide equals an ether. If we go through the mechanism of this, it's simply just an SN2 reaction like we've seen before. So using pH to represent phenyl, draw out my alkoxide anion, sodium doesn't mean anything. Draw out my alkyl bromide, this is my electron-rich species. This is partially positive because it's attached to the bromine. So an SN2 reaction, and we get to our product making an oxygen-carbon bond. This reaction is useful for making cyclic ethers that look something like this. And so we call this an intramolecular reaction when we have a reaction within one molecule. An intermolecular reaction is when we have a reaction between two molecules, which is what we usually see. And so in this case, we have a nucleophile and an electrophile in the same molecule. Remember, oxygen's not that nucleophilic, so we need to deprotonate it first. So we throw in potassium hydroxide. And so if we draw out the mechanism for this reaction, I'm going to draw out this hydrogen. Potassium doesn't mean anything, so we draw out hydroxide, and then this is going to deprotonate our alcohol, giving us our alkoxide, which I mentioned a little bit earlier. And so if we draw out this intermediate, we get to something that looks like this. And so now we have a pretty strong nucleophile, an electrophilic carbon, and so we do an SN2 reaction within the same molecule. And so we call this an intramolecular reaction, and then this gets us to our final product via this SN2 reaction. Remember to count your carbons. So here we have 1, 2, 3, 4 carbons. 1, 2, 3, 4. Also follow what you're doing. This oxygen is still attached to this carbon, attached to this carbon, attached to this carbon, and then the oxygen is now attached to this carbon as well. And this carbon is no longer attached to the bromine, so we get a cyclic ether product. And so this can be especially useful for making epoxides. Epoxides are these three-membered rings shown here with the oxygen in the middle. And so this is the epoxide. And we can make these from these special alcohols and alkyl halides. We call this, when it's a 1-2 relationship between the alcohol and the chlorine, we call this a halohydrin. Halo for halogen and hydrogen for the oxygen. In this case, we see that if we go through the same mechanism as we did earlier, this oxygen would be deprotonated by sodium hydroxide, then make a bond to this carbon, kicking out the chlorine in an SN2 reaction. And so 1, 2, 3, 1, 2, 3, we make this epoxide ring. Before I continue talking about epoxides and why they are important, I briefly want to mention that these reactions can also proceed under acidic conditions. So everything you've seen, we've used potassium hydroxide or sodium hydroxide or something like that. So basic conditions. I'm only going to touch on this for a second. Acidic conditions are not very useful because we can only make symmetric ethers. And so you essentially take two of your starting materials to make one of your products. And so you can see that it's symmetrical, it has a plane of symmetry. 1, 2, 3 carbons on this side, and we add it to both sides of our ethers. So again, not very useful, but it is possible. Alright, so back to talking about epoxides. Why might we want to make epoxides? Keep in mind that epoxides look like this, so they are a three-membered ring. And remember, three-membered rings, these bond angles right here are 60 degrees. This is a sp3 hybridized carbon, so it's tetrahedral, and so the ideal bond angles are 109.5 degrees. And since this is not the ideal bond angle, these carbons are very reactive, and so they act as carbon electrophiles. And so this allows us to treat epoxides with several different types of nucleophiles. And so we can make new carbon-carbon bonds, carbon-halogen bonds, carbon-hydrogen bonds, carbon-oxygen bonds, or carbon-nitrogen bonds, depending on what our nucleophile is. So keep in mind that epoxides are ethers, just like this acyclic ether drawn up here, but there's no ring strain built into this type of molecule. And so if we try and do an SN2 reaction, remember that oxygen is a bad leaving group unless it's protonated. And so in this case, no reaction is going to take place. But since epoxides have 60-degree bond angles, they're very reactive. And so if we treat it with the same conditions, we will get a reaction opening up this ring, giving us this alcohol and a halogen on the other side. So let's first look at making carbon-carbon bonds using epoxides. And so if we take this epoxide, we know this is an electrophile, so we need to treat it with a nucleophile. Up here I have this alkyl lithium compound. Remember that lithium doesn't mean anything, and so we mark it out and put a negative charge on whatever's next to it, which would be this CH2 here, where the negative charge is on the carbon. So this is our nucleophile. It comes in and attacks here and opens up this ring to give us a new carbon-carbon bond between this carbon and this carbon. And so in total, we have 2 carbons here, 2 carbons here, so we have 1, 2, 3, 4 carbons in the product. Likewise, we could use this Grignard reagent here. So we have magnesium bromide. Remember, this doesn't mean anything. We can mark that out and put the negative charge on the carbon that it's attached to, making it a nucleophile. And so this would come in and do an SN2 type reaction similar to our alkyl lithium up here, giving us a new carbon-carbon bond from this carbon to this carbon. And so again, count all of your carbons. You have 6 in this ring here, 7, 8. We have 6, 7, 8 shown here. And then you might notice that I have a step 2 written down here and down here. And both of these are the same. They are HCl and H2O. And we call this an acid workup step. And so this is very important for doing these types of reactions in the lab, and so we need to include it even when we're writing it on paper. And I'll talk more about what an acid workup step is in just a second. So let's go through the mechanism of the Grignard reaction. So remember that when we look at this, we go to step 1. Magnesium bromide doesn't mean anything. That just means it's the carbon it's attached to is negatively charged. So we can mark that out. Put a negative charge on that carbon, so that acts as our nucleophile. Our epoxide is in our electrophile, so we go electron rich to electron poor, and we open up this ring. What does this give us? It gives us a new carbon-carbon bond from this carbon to this carbon. So let's draw out that intermediate. This oxygen is still attached to this carbon. It also got an extra pair of electrons from here, so it has a negative charge. It's attached down to this carbon, which is still attached to this carbon. And then this carbon is now attached to the phenyl ring. And so we draw that out. Again, making sure we count our carbons. We have 6, 7, 8, 6, 7, 8, plus the oxygen. And so this gets us to our intermediate. Like most of organic chemistry, we just need to follow where the electrons are going and where they would be most stable. And so think about this negative charge here. What is the pKa of the conjugate acid? And so the conjugate acid, remember, is just adding a proton. And so if we take this negative charge, we add a proton to it, that gets us to our conjugate acid. I'm just going to draw out this one hydrogen here. pKa of this is about 42. And so pKa of this is 42. And then here, what's the pKa of the conjugate acid of this? Conjugate acid would be an alcohol, and so an alcohol pKa is about 16, and whoever has the lower number is more happy with the negative charge. And so essentially when we do this type of reaction, we've transferred this negative charge from here to here. Where does that negative charge want to be? It wants to be here, and so the reaction proceeds forward. All right, so once we're at this point, then this just sits around forever because this is not an acid, right? So there's no protons floating around. So this sits around forever until we protonate this to get to our final organic molecule. That is where step 2 comes in. And so HCl and H2O, I'm going to draw a reaction over here off to the side. So HCl plus H2O. Think back to like general chemistry. So this gives you H3O plus Cl minus, right? And so if you want to think about the equilibrium of this reaction, you want to identify the acid on both sides. Acid on this side is HCl. pKa is about -7. And then the acid on this side is H3O plus, where the pKa is -1.7. Remember, whoever has the higher number would rather have the proton, and the equilibrium lies towards the higher number. Negative 1.7 is the higher number, and so the equilibrium lies this way. And so usually when we have HCl and H2O, we just write it out as H3O plus. So with that in mind, we're going to draw out H3O plus. This hydrogen here I've drawn out from the oxygen because it's going to participate in our mechanism. So we go from electron rich to electron poor. We have a proton transfer reaction. We grab this proton and we kick off water shown here. And so this gets us to our final organic molecule. That looks like this. And so now we've gone from a negatively charged molecule to a neutral molecule. And so workup is important, this acidic workup right here, and it helps us to get to a neutral product molecule. And so keep this in mind when we're doing a lot of reactions. The last step you're going to see is HCl and H2O. You might just see H3O plus written. All of these are workup steps, and they simply protonate the negatively charged organic molecule that we get from our first reaction. So let's take a look at making carbon-hydrogen bonds using epoxides. And so we see here we have an epoxide. We know that acts as an electrophile. And so in step 1 here we have sodium borohydride written out. If you remember from a few weeks ago back in class, sodium borohydride equals H minus. And so in this case, H minus acts as a nucleophile when it's attached to the boron species. So it comes in and does an SN2 reaction, just like we saw the Grignard reagent do. This pops this open and then gets us to our product over here after our acidic workup. And so if we actually draw out what happens here, we've transferred this minus charge from the hydrogen to the oxygen. And so we've opened up this ring, so we have something that looks like this. I could draw out the hydrogen and just attacked. I don't have to. I could just leave that off. And then this floats around forever until we throw in HCl and H2O, which we write out as H3O plus. We get a proton transfer reaction to get us to our final product. So it's very important that you remember that lithium aluminum hydride and sodium borohydride equal H minus, and it acts as a nucleophile, and that's because of its electronics when it's bound to the aluminum or boron species. And then sodium hydride acts as an H minus base, and so don't get these two confused. Use sodium hydride when you want to use a base. Use lithium aluminum hydride and sodium borohydride when you want to use H minus as a nucleophile. So let's talk about the stereochemistry, so RNS kind of things, diastereomers and enantiomers, as well as regiochemistry. And so remember, regiochemistry means we could have a methyl group on one part of the molecule or a different part, and so we call those constitutional isomers. And so regio meaning the region of where a particular thing is located. I've been drawing epoxides that are symmetrical, where we could attack either side and it really didn't matter because they both had two hydrogens on them. But what about if we have an epoxide that is not symmetrical, it has chiral centers? What is the outcome of these reactions? Well, if we are under basic conditions, we take sodium methoxide shown here. Remember, sodium doesn't mean anything. We end up getting this as our exclusive product, where we have the possibility of attacking here or the possibility of attacking here. In the case of basic conditions, we get attack exclusively at this carbon shown here. And so this is our only product that is obtained. If we go through the mechanism, we want to draw out sodium methoxide. Sodium doesn't mean anything, or ethoxide, sorry. And so we have our nucleophile. We know epoxides act as electrophiles. And so which side do we want to attack? When we're under basic conditions, we're going to attack the side that is least hindered. So this side has an ethyl group and a methyl group coming off. This side has a methyl group and a hydrogen coming off. So this is less substituted, and therefore it's going to be easier for our nucleophile to attack here. And then this opens up our ring, giving us an intermediate that looks like, let's see here. looks like this shown here. And so our oxygen has made a new bond to this carbon. So we've made this new oxygen carbon bond shown here. And then we broke this oxygen carbon bond, giving us a negative charge. This then floats around forever until we do our acidic workup. And so we draw H3O plus again. And we do a proton transfer reaction to give us our neutral organic molecule. You also might notice that this is an SN2 reaction in this case. And we know that in SN2 reactions, we get inversion of stereochemistry. And so we take a look at our RS designation of this chiral center shown here. We know that, let me get rid of these mechanism arrows so it's a little bit easier to see. We know that we have a hydrogen going away, and so that would be priority 4. Oxygen would be priority 1. This stuff over here would be priority 2, and then our methyl group would be priority 3. 4 is already going away from us, and so we see that this is 1, 2, 3, and so it would be R. And then if we look at our product material over here, we look at this stereo center right here. We know that we have a hydrogen going away just like we did before. This would be priority 4. Oxygen would be priority 1. This stuff over here, priority 2. And this methyl group, priority 3. 4 is going away from us. We go 1, 2, 3, and we see that this has S stereochemistry. Since it's an SN2 reaction, we have inversion of the stereo center. So we go from R to S. Then if you figure out this stereo center shown here, nothing happened here, and so it should be the same as over here, where in both cases they are S. Let's figure it out while we're at it. So oxygen would be priority 1. Again, we're looking at this stereo center here. Oxygen would be priority 1. Methyl group would be priority 4. This stuff would be priority 2. Ethyl group would be priority 3. 4 is going away from us, and so we have 1, 2, 3. That would be S for this stereo center right here. And then if we look at the one over here, the way I've drawn it, oxygen would be priority 1, methyl group priority 4. This stuff over here, priority 2, and the ethyl group, priority 3. 4 is going away from us. We go 1, 2, 3, and we see that this stereo center is still S. So again, where our reaction took place, we have inversion of stereochemistry because it's an SN2 reaction. So we go from R to S at this reaction center. The other center has not changed, so it's still S in both cases. So keep in mind that under basic conditions, a nucleophile will attack the less substituted carbon from the opposite side of the epoxide oxygen. So that's our leaving group. And so we get an SN2 reaction, inversion of stereochemistry. Under acidic conditions, we get the opposite reactivity. So basic conditions attack the less substituted side. Acidic conditions, we're going to attack the most substituted side. So in this case, we use strong acid, HBr. Bromine ends up being our nucleophile, and so it adds to the more substituted carbon. So this is different from the basic conditions. If we go through the mechanism, we know that proton transfers are extremely fast. HBr is a very strong acid. It wants to get rid of that hydrogen. And so the first thing we're going to do is protonate our oxygen using HBr. And so this gets us to an intermediate molecule that looks like this. The oxygen is going to have a positive charge because it now has 3 bonds. And so at this point, the oxygen, since it's positively charged, it wants to suck electrons away from these 2 carbons. And so essentially, this is not the actual mechanism, so I'm going to draw it in a different color. But this is the way you should think about it. Since it's pulling electron density from both carbons, you want to think about which carbon could handle a carbocation better. So if it sucks most of its electrons away from this carbon, that means we would essentially break this bond here. That would give us an OH. Let's see here. And so since we pulled electrons away, we now have a carbocation here. We see that this is primary, and so it's not stable at all. But if we suck more electrons away from this carbon, then we have this type of carbocation because of this additional methyl group drawn down here. This is secondary, and so this is more stable, meaning that this carbon can handle a positive charge more so than this one, and so our reaction would take place here. Again, drawing these carbon-oxygen bonds breaking before the nucleophile attacks is not part of the mechanism. It's just a way for you to think about what product you're going to get. So which carbon can handle the positive charge better? It's going to be this one here. So our nucleophile, Br- comes in and attacks, again, popping this open. And this occurs via an SN2 reaction. If we draw out the product of this, we get all the way to this molecule shown up here. Since this is SN2, we're going to get inversion of stereochemistry. And so if we think about this chiral center right here, we know that we have a hydrogen coming towards us. That's going to be priority 4. Methyl group is going to be priority 3. Oxygen is going to be priority 1. And this stuff coming over here will be priority 2. Number 4 is coming towards us, so we need to say the opposite of what we see. It looks like S, so it would actually be R in this case. And since we did an SN2 reaction, we should have S drawn on this side of the arrow for our products. So get rid of this arrow here. We have a hydrogen that's coming towards us. We still have this methyl group that's going away. Hydrogen's priority 4, methyl group priority 3, bromine priority 1. This stuff over here, priority 2. 4 is coming towards us, so we want to say the opposite of what it looks like. And so it looks like R, but it's actually going to be S. And so again, we went R to S because we went through an SN2 reaction. So just keep in mind that under acidic conditions, a nucleophile will attack the more substituted carbon from the opposite side of the epoxide oxygen. And so this goes through an SN2 reaction. We attack the more substituted carbon and get inversion of stereochemistry.